everybody of you will certainly know him. Sean is known for his many contributions in applied probability. He's been working on a broad set of problems. Today he's going to talk about, what is it, Sean?
Can we simulate estimate the mean Q size?
Can we estimate the mean Q size? Every one of us thought we could, so please tell us about it.
Thank you, Michelle. Thanks so much. Yeah, it's wonderful to be with so many friends, and I really am very grateful to Soren and Peter for putting on this show. It's fantastic. So actually, I mean, maybe we can all just go home because, as somebody mentioned yesterday, I'm talking about just trying to estimate the average Q size, say an MM1Q, and that's not a large deviations event, so it's complexity big O of 1. So that's the end of my talk. So this is a joint work with Ken Duffy, who's here, and Yanis Kontiyanis at Athens. I forgot to mention him there. And so actually this work is really based on my book with Richard Tweedy on Markov chains and this new book on control techniques for complex networks. And we can skip the rest of this ad. But so here's the outline. So I really am going to just be looking at trying to estimate the mean of a queue through Monte Carlo. And we all know that it is hard. I mean, it's heavy traffic theory to explain that, and I'll review that in the talk. But there's also some other really exotic statistics in just this simple exercise of estimating the mean of a queue. And it turns out, I'll use that as an example, but the same is true for MCMC and for queuing networks and all sorts of different problems. So it's, I don't know. And I'll try to make it as entertaining as I can because it is late in the day, so lots of pictures. So it turns out that this is actually a histogram obtained from looking at repeated estimates of the queue length in an MM1Q. And you see it's very lopsided. It looks Gaussian, but it's sort of tilted and fat on one side. So I'll explain why that's the case. And then there's some nice large deviations theory and understanding when you get bad overestimates of the mean queue length. And I'll wind up with some conclusions. Okay, so let's just stick to the MM1Q for most of this. I mean, it's the nicest Markov chain in the world, right? I mean, it's reversible. It's skip-free, which means that it can only jump up or down by one step. It's monotone. If you start with two initial conditions, one above the other, they stay ordered forever, which is a fantastically powerful tool. As Jeffrey Rosenthal pointed out, under monotonicity, you can get very accurate estimates of the rate of convergence for a geometrically ergodic Markov chain. So it's fantastic. But as we all know, it's very hard to simulate. If you estimate the steady-state customer population in a queuing network, it can take a long time. And let me give some history. So one is it's been known forever that there's a large variance. Well, actually, I'm jumping ahead. But sorry, let's stare at this for a minute. Okay, so before I go on, so this is actually from chapter 11 of this new book. Now, that is the Gaussian density which is predicted by the central limit theorem. Okay? And what I've done is I've taken 100,000 samples, and I'm looking at the central limit theorem. This should be approximately Gaussian for n equals 100,000. And basically what this is a histogram of 1 million replications of that experiment. And so you see that, yes, the histogram does seem to fit the Gaussian density pretty well, but except it's got this heavy tail on the right, and on the left it looks like the tail's lighter than you'd expect. And the whole thing looks sort of shifted, actually the other direction. Okay. And so, simulating queues is one thing. Also, we'd like to be able to use Monte Carlo in learning algorithms. I mentioned in one of my questions TD and Q learning, and there this effect is getting multiplied through these in these algorithms. And so understanding why we get such horrible high variance and sort of heavy-tailed looking behavior, even in a light-tailed model, is worthwhile.
The initial condition here, right?
0.
For the Gaussian, is that based on the stationary distribution?
Oh no, this is the so the central limit theorem holds for any initial condition.
Yeah. The centering would depend on where you start from.
No, I mean
whether that's settled the stationary or not.
Well, but the mean by 100,000 samples. I mean.
Depends how long.
Oh, I see.
Runs. Yeah, right. So.
Yeah, Well, it's just yeah, I guess so. No, but if you look at this, oh, I see what you mean.
Yeah, you might
Oh, I
just
didn't know.
not
It's funny that I never even noticed that. It's funny that it's shifted way over. Yeah, maybe a different century would make sense, but yeah. No, but yeah, well, yeah, the peak is flipped over. The area here, yeah, it's just not symmetric. Yeah, no, it's, yeah. I mean, I don't know if that's a major fact. It's mainly the strange shape that's important here. Okay, so now I want to now explain this. Now I'll give some history on why we expect a large variance, but there's much more that I'd like to talk about. Okay, so let's look more generally just at a reflected random walk. The new state is the old state plus an ID increment max with 0. And we've got an initial condition, and this is a nice Markov chain. The only thing I can assume is that it's got negative drift and a finite second moment. Under those conditions, we know there's a finite steady state. It's a Harris-ergodic Markov chain with a finite steady state mean Q length. And one example, of course, is the MM1Q, where this delta process is just goes up with probability alpha and down with probability mu. That's an MM1Q obtained from sampling using uniformization. We want to use basically the basic question I mentioned is that I've got this quantity I'm calling eta, which is a steady state mean of this Q or reflected random walk. And again, I'm just using standard Monte Carlo to estimate the mean. And we all know, yes, it does converge and the CLT holds and all of that. Okay, so just burn that into your memory. Eta n just means the standard Monte Carlo estimate of the mean state at time n. Okay, so first of all, variance. So it's been known at least since WIT 1989 that the variance is huge. So first of all, in order to get a central limit theorem, you need a third moment for these increments. And under that condition, the asymptotic variance is like 1 over 1 minus 0 to the fourth power. So the standard deviation is 1 over 1 minus 0 squared. And that's at least 20 years old. So then if you go back and look at this, if you look at the standard deviation, maybe that's about 200 or so. Right, something like 200. This is an example where the network load is 0.9. So 1 over 1 minus 0 squared is about 100. Right, well, exactly 100. And so this is actually very consistent with the theory. Okay. What about large deviation? So this is supposed to be about rare events. So let's talk about that. So again, I'm assuming only a negative drift and a finite second moment. So I might not even have the central limit theorem. So might not even have a third moment. Okay. But even so, even under those very weak conditions, I might not have a third moment. I still know that actually there's a beautiful large deviations limit. And I believe a Bahadur limit as well. I mean, very fine asymptotics. And that hasn't been proven, but I'm almost sure that you have an exact, you don't even need a logarithm here. You have an exact LDP. Okay? So that's from a paper about 5 years ago. But for the upper tail, it's null. So if you look at the probability that your average is bigger than R, for any constant R which is bigger than the mean, that goes to 0 sub-exponentially, as n goes to infinity. We think we probably have to divide by square root of n here instead of n, but we don't know. Okay. All right, so that explains a lot. The fact that we have this sort of heavy-tailed behavior on one side and light-tailed on the other really definitely explains a lot. And this is exactly what you'd expect it to be. So if you've got a third moment, if you can do a Taylor series expansion, it's going to look quadratic when near r equals its minimum, and its second derivative will be the central limit theorem variance. It has, the lower tail is exactly what you'd expect it to be, but the upper tail is null. Okay, and that's it. So that explains why you have the fat tail on one side and skinny on the other. Yep. Yeah, I said burn that in your memory, but yeah. Oh, wait. I need an eraser. Yeah. Oh, okay. All right. So, well, anyway. Okay. So that's the only thing you have to memorize in this talk is the eta n is the average of the state. All right. Okay. So why? All right. Why? So why is it that we have? I'll try to explain everything. So I'm going to try to explain why we get a Lyapunov LDP for the lower tail, no LDP for the upper tail, and actually try to get a better idea of what happens in this more this strange situation here. So why so lopsided? First, let's look at do the standard trick. Let's look at this twisted distribution. Now, if you haven't seen this before, just go to sleep for a few minutes. There's no way I could explain it in 5 minutes. But you take your transition kernel for the reflected random walk, and you multiply by e to the theta x. Well, I'm going to take theta negative. X is the thing I'm trying to estimate. X. And subtract off that's a log moment generating function. Hope it exists. Okay. And what this function is, it's a function such that this becomes a transition probability. It actually it's a solution to an eigenvector problem. Okay. And what you can do is you find, and I have a lie here, I haven't proved this. What you can do is for theta negative, you can actually find this function f check. And this twisted kernel is geometrically ergodic. It's more than that, it actually satisfies the conditions of Donsker and Veridon. Even though the original chain might not have even been geometrically ergodic. You might have only had a second moment for the increments. So you wouldn't even be geometrically ergodic. But the twisted kernel is the most beautifully ergodic chain you can imagine. And from ergodicity of the twisted chain, you can prove large deviation asymptotics. The Bahar-Durao business is a conjecture, but based on joint work with Kantianis. I'm pretty sure it's true, but it hasn't been proven. Okay, so again, this is only possible when theta is negative. And the reason is that you've got the e to the theta x, theta is negative. So for large x, you're basically truncating the kernel, you know? So it's almost like you're making it a finite state space Markov chain when theta is negative. That's the idea, you know? And by that's a completely general result. I mean, you can take a positive recurrent Markov chain, not necessarily geometrically ergodic, and if you're looking at the simulation of a coercive function, a function which blows up for large x, then you get the same trick works in very, very broad generality. That's what's in this 2006 paper. Okay. So what about when theta is, what about upper large deviation? So here I was looking at the lower tail. That's the red circle there. What about the upper tail? Okay. So this is the fundamental theorem of triangles. You all learned this in probably one of these workshops once. This gives it away, I hope. Maybe not. That does. Okay, so we all know because of Venkat, the way in which Q's get large. You know, they basically act like, you know, there's a triangular shape. Maybe not an isosceles, but given the fact that you get a large value of the state, you go up at a roughly linear rate and you go back down linear. We've seen that over and over again in even today's lectures. And it turns out that my definition of eta n here, right there, which is just Monte Carlo, that turns out to be n inverse times basically area of this region. You know? If you look at the area under this strange region here, which is approximately triangular, eta n is just 1 over n times a. And if you actually just work out the algebra. And so that's really it. So if you actually then think about it, if I look at the thing that I know that the probability, I've got this large deviation probability for the probability that x reaches a value, say gamma n, before time n. That has some sort of rate function. And if you think about what that means, let's go and translate that. It means that eta n is bigger than some constant times n. One more time. Eta n is n inverse times a. And if I go through and I say that x reaches some height gamma n by time n, I'm going to choose a value there. That's the same as saying that eta n is bigger than this scaled area. Yeah. And you just go through and look at that. We've got, that's, let's say, equal to this. And so this is greater than or equal to the probability that x reaches height gamma n just by looking at these asymptotics, by knowing the fact that we have these triangular asymptotics. So I'm saying basically I reach gamma n and I just have this triangular shape, roughly speaking. So it's just algebra here, but sorry. Yeah. Yeah. Yeah.
I can understand the occupation measure stuff not requiring any assumptions on the moments.
Yeah.
But the sample path.
Oh, yeah, this is different. Oh, no. Right here, I'm going to assume more, absolutely. So I haven't gotten to the assumptions I'll impose yet. So here, I'm just want to give you the idea. So yeah, here, assume everything you want. Assume it's M1, whatever you want. So here, I'm just trying to give you a lower bound, and then I'll give you assumptions in a moment for final results. Okay, so again, so here I'm looking again at the probability that the estimates are not bigger than a constant, the question you normally would ask in large deviations. All right? I'm asking what the sample path average is bigger than a constant times n. And that I find is lower bounded by something, negative. And so you can imagine if I let gamma now go to 0, that's going to go to 0, and that's why I get a null large deviation principle. This is true for any gamma, so now let's let gamma go to 0. And so I get that this lim in for this quantity is greater than or equal to this quantity for any gamma, and so therefore the lim in for this is 0. That's exactly the null large deviations principle. Okay. In fact, I should say this a few more times. Yeah. But I've got a lower bound here, which is holds for any gamma. And so imagine now if I look at the probability this is bigger than a constant instead of something that's blowing up with n. This is not the large deviation question that we had in mind, right? In large deviations, you're asking, what's the probability of being bigger than the mean value plus a constant? Not something that's blowing up with n. Okay, so that immediately applies at the large deviation, the upper tail large deviation principle is you have a null exponent, it's a 0. Okay. All right, now let's understand it. So now let's think about, given this event, let's just say that given the fact that my estimate mean Q size are not 10% bigger than the mean, but actually blowing up, actually of level n, and when they're supposed to be rho over 1 minus rho. Given the event that my estimates are just blowing up, what is the Q doing? What's going on? Let's ask that question. That's the appropriate question for this workshop, right? So now we can talk about rare events. So this is it, right? Vacant. We all know that when a Q gets large, it goes up linearly and it comes down linearly.
I mean, that's known ages ago, right?
Yeah.
My paper was more about heavy tail.
But you're wrong. No, so you can think about it. So we're trying to think about a large area, which means a large mean Q size. And if somebody told me a triangular path was optimal, I'd say, well, look, I can just make it a little fatter, just I'll make it strictly concave here and here, at almost no cost at all, in terms, given the right large deviations assumptions on the increments. The cost of this path is almost the same as the cost of the triangular path, but the area is much bigger. And from that, you can deduce that actually most likely paths are strictly concave, and there might be a linear bit and then strictly concave. Okay. Can you see that? Basically this path has very much the same probability as the piecewise linear path looked at in your work, and looked at by many people here. But by making concave, a little bit concave like that, I get much bigger area. And so that's why you do not get piecewise linear trajectories. Given a large value of the sample path average, the most likely trajectory becomes concave. All right, so what is it? So to analyze this, let's go look at the usual fluid scaling. So I've got x of nt divided by n, and I want to look at a large deviations principle for this process. Yeah. What?
Different question, it's a different answer.
Yeah, I know, of course. Just trying to wake you up,
Not easy.
Yeah. And so the question I'm looking at now is that a to n is approximately equal to an. A is this area, basically, for the scale process. And so I'm looking at this fluid scale process, so that's approximately a. And I want to look at this standard large deviation principle, basically, the most likely behavior given this constraint. And now we have to put in some assumptions. So I'll assume that my increment process, that we satisfy a large deviation principle. So I can justify look at the problems that we've looked at today. Okay, so it wouldn't even have to be IID, of course. It could be something else. Okay. So now what I have is I have an optimization problem. I have this rate function now, which has some sort of a cost for a jump at time 0. It might be that the scale path jumps up at time 0. And then there's a integral of the rate function, the local rate function, evaluate the derivative of the path from 0 to 1. And I'm going to restrict to functions psi that are concave because you can prove separately that they have to be concave. Right? You know, without downward jumps. So that's an assumption we can impose. Okay? So we get an optimization problem. We want to minimize this rate function. You know, the cost of the jump at time 0 plus this the total cost of the path, but subject to an area constraint for psi. And so we can go through this step by step. I mean, you're looking at structure of this, but actually it's a beautiful it has a beautiful solution. And it's simple enough that you can just write it down. So let's do it. Si se puede. So first of all, you just do integration by parts up here, because what I'd like to do is get this as just a function of psi dot. And if you go around and look at that integral and play around with, this integral, and you play around with integration by parts, we can replace it by something that is a function of psi dot instead of psi. And then there's a Lagrange multiplier lambda, which I don't know, but we'll figure it out later. Okay? And now stare at that for a moment. I've got two independent variables. I've got my initial jump, and I've got psi dot. And I can just go around now and play around and use just perturbations. And look how simple it is. You know, if I look at perturbations, I'm going to get a lambda t here, you know, by looking at a perturbation of psi. And I'll have a gradient of the local rate function here. So I'll have to assume this local rate function is differentiable. I mean, it's, you know, I'll have to justify a few things, but it's going to be convex. And there we have it. What we end up finding is, well, first of all, I mentioned the optimal paths are concave. And what we find is, from what I was saying here, I get a t and I had a t times lambda here and a gradient of I here. That's the formula you get for optimal path from perturbation. Okay? So just by saying I've got a local optimizer here, if I perturb psi, I get that the gradient of this term plus lambda times t is 0, or minus lambda times t is 0, which is what this is saying. I think there might be a sign change there. Yeah, that should be, I mean, anyway, it's a matter of sign conventions there. Okay, and the constant b there, you know, it's just a constant. Right? Now that's only true if it's a local optimizer. Okay, so I have to argue that there's an initial time here where it's a boundary optimizer. I'm actually going at maximal slope. Like for an MM1Q, that maximal slope would be 1. Okay, but from this point until I recover, or time 1, that's I can look at perturbations in that interior, and that's where I get this differential equation. Yes. That's the cost of a jump. Oh, what is it for? So I mean, it's infinity for if the increments are Gaussian or bounded, but for an exponential, you can come up with a formula for it. Ken, do you remember what you're there? Okay.
It's the maximum tilt that you can make to the moment generating function.
Yeah, that's right. Yeah, it's where the
It's the exponential rate in an exponential.
yeah, it's where the log generated function blows up. That's right. So it's just no, that's not right. Okay, never mind. Where the log generated function blows up. I haven't thought about that for a bit now. So anyway, so that you can deal with separately. So you can deal with the jump separately. The main thing that's important is understanding the behavior here, and there it is. It's just a simple formula. It's wonderful that you can actually just write it down. And so for different processes, you'll get different behavior. So, okay, so here's some examples. So it turns out that if you actually look at this rate function, it's a function of a. When a is very, very small, it looks like a square root. You know, I think that's consistent with some conjectures we have about other dynamics. But anyway, so I think that's always going to happen. You're going to get this concave behavior initially, and then it blows up. It looks more convex for large a. So that's the rate function. You know, this rate function evaluated at the optimal trajectory, and so it's a beautiful non-convex rate function. Here's a function of a, but it's beautifully non-convex as a function of a. And here are the most likely paths. So for this M1Q, for a very large area, you see you're going up at slope 1, that's the maximum slope for a simple Q, and then you get a concave behavior at the end, when A is large. For smaller A, you just get this smooth curve. For Gaussian and Poisson, you just always get smooth curves. There's no maximum to the slope, and you can never have a jump. For geometric, it's the only case here where you see a jump. For a very large area, we see a jump, then a concave behavior. And there's no bound on the slope, so you'll never see a linear piece. All right. So there you have it. That's it. We can all have a beer. So just a wind up. Amazingly, I never would have dared to do this, but I never would have dared to look at this problem in any case. Ken Duffy thought we could do it, and it turned out to be much easier than we thought. But to actually try to simulate this is looking at a simulation, looking at 10 to the 8th sample paths, and picking the results with the largest area, and then plotting the resulting state process. This is for Gaussian increments. This is the MM1Q, and it really is, following that most likely path. It's the theory works. Okay, so the conclusion. So again, it's been well known to all of us that simulation is hard, and we know this from heavy traffic theory, that we have this 1 over 1 minus rho squared standard deviation for simulating networks or queues. But this load, that's in heavy traffic. Here, this is for any load. Load could be 0.1, and we would still get this heavy tail behavior on one side and light tail on the other. And so it's very different than anything I've seen before in buffer overflow analysis. In terms of other Markovian models, what happens then? Unfortunately, I gave away the punchline, but it's right there. So I said that the MM1Q is the nicest of Markov chains, and it is very, very nice, except that skip-free property, the fact that you can only move up by 1 step or down by 1 step, is the reason for these problems. And the same is true of the Hasty Metropolis algorithm for MCMC, and for stochastic approximation with bounded right-hand side. All sorts of models that we look at have the exact same property of being either skip-free or skip-free the mean, which means that the expectation of xt minus xt minus 1, the increments of the process, have a uniformly bounded, say, first moment over all initial conditions. It's that skip-free property that enables all this beautiful theory, like the fluid model approach for stability and all of that, but it also creates this barrier for simulation. Let's see. So, in terms of questions, one of you might want to look at heavy-tailed or long memory settings. I doubt that that's something that I'll be able to look at in the near future. Variance reduction is fascinating because this is an example of simulating a queue with a burstier arrival process. And what you can do is you can look at control variates. So we know that control variates are useful for variance reduction. You can look at Soren and Peter's book. But also we know the fact that if we simulate a function which is coercive, which is blowing up, then we get large deviation estimates for lower tails. So why not construct 2 estimators with 2 different control variates? One satisfies an LDP for one tail, and the other satisfies an LDP for the other tail. And what you end up getting is sort of a random confidence bound, where the mean is very likely to live within this region, because this estimate overestimates the mean, and this one underestimates the mean in the sense that I've talked about in this talk. This satisfies a large deviation principle in the positive direction. This upper one satisfies an LDP in the lower direction. So there's a lot of ways of doing this right, and lots of different models, and in particular MCMC. How would you do it there? And just an advertisement. This is work with Shane Henderson, Peter's student, where we just use some very naive models to construct control variates, and we're able to get 100-fold variance reduction in networks. This is an example. These are just parameters in a control policy. And so, so control variates are something that are much easier to construct than importance sampling estimators. And so there is a lot of potential applicability here. Not that there isn't for importance sampling, but it's more ready to be applied. Lastly, there's a conjecture here which may be trivial, I don't know, but perhaps by the end of the week we can take care of this. If we look at the thing we really care about initially, which was the probability that the average of the Q exceeds some constant R larger than mu, it seems to go like 1 over square root of n, and I'd like to know what the rate function is. My conjecture is that this sort of has a square root of our shape, but I'm not sure. And I can't tell if it's easy or hard, so it's a fun problem for someone. Anyway, and that's it. So the end has some references. Thank you for your attention.
Thank you very much. Are there any questions to Sean? Peter.
More of a comment that when there are wide deviation results that you can sort of similarly think as that have to do with things like you look at the tail of the integrated workload inside a busy cycle.
Oh, right.
You can do asymptotics with that. And there's sort of a matching with your square root in the sense that you look at that the tail of that random wheel, and that looks like a wheel with a square root.
Okay. All right. Thank you.
Any other questions? Yeah.
Yeah, I'm interested in the light tail case, like infinity Q or something like that.
Oh, right. Okay. Good. Thank you. So, yeah, that's a great question. So, if you take something like the infinity Q, that's very much like a linear system, like a stochastic differential equation where A here has its eigenvalues in the left-hand plane. That satisfies the conditions of Donskian Varadon, and there everything looks beautifully. So yes, when you have a linear drift like that, that's when the drift grows linearly with this state. That's when you have everything is just as you expect.
For the MG infinity Q, you can explicitly compute the full distribution actually of the area below the graph.
So even in that case, it depends on how fast that function
Which function?
So if you look at index that are powers.
Oh, certainly. Of course, there are limits on what you can. Oh, of course. So the result is. All right. Shall I? I've got time. Where's an eraser? Is it? Oh, right there. Is it chalk?
Down below, I think.
Is it?
Should be in the.
Here we go. So for the infinity Q, you could solve a drift condition like this. PV is less than or equal to e to the minus f plus b indicator function c times v. How's that? So v is a Lyapunov function that blows up. PV is the conditional expectation. F is some coercive function, something like epsilon x squared. C is a finite set, and there's my function v again. So if the function I'm trying to simulate I hope that's big enough. I didn't give myself much space. But if I look at the average of some function g, as long as g blows up more slowly than f, then I've got all these beautiful exact logicalization asymptotics. And so for g sub quadratic, I know everything works.
So, I mean, something else which is similar to that, but it's going to be different, I think. I'm more interested really in Metropolis with light tail distributions, right? So that's not going to be like this or like so if you look at the large deviation patterns.
So I wish I had a copy of the new edition of my book. I mean, not for advertising, but I'm serious. Let me just go back. This is worthwhile because if you look at hasty Metropolis, it's a skip-free Markov chain in the sense that the increments are bounded in mean square, and you can't see it. But actually, what I wanted to get here was that this is actually these lines here that cover my book are actually level sets that define a fluid model for hasty Metropolis algorithm. And so, trying to compute the most likely paths will be much more exciting than what we have here. But definitely, it'll be something like. You can't see it, but I'm sure you can get some qualitative insight into what they're like.
So my intuition is that it's a bit different in that case because, I mean, I might be wrong, I haven't
Yeah.
thought about it in this way, but your paths aren't going to want to look concave in that way because
Yeah.
because as soon as they get up there, I mean,
right.
in the geometric tail case, it doesn't really matter where you are. In some sense, you're being penalised by the model in the same way.
Yeah. So the main point is just this, that for MCMC we get the same horrible behavior, that the probability of being, like if you take again just the state, the average in the state, the probability of making the constant times n is going to, you're going to get bound like this, but the actual most likely paths could be quite exotic. I don't expect I can compute them. But at least the fluid model has a nice form, so in some cases you might be able to.
So at least one side of your conjecture is kind of obvious, right?
Well, getting a bound, getting a bound, I think.
Yeah, getting
yeah.
low bounds kind of
But
obvious.
is this the rate function is what I don't know is easy or hard. But,
So the problem
yeah.
is you might have to deal with some kind of local characteristics of the increments that aren't in the loss deviations regime. So
yeah. I haven't, frankly, I haven't thought about it enough, but yeah, but that's I thought it, but yeah.
Other questions? Well, I had a few. First,
So in this averaging, if you skip a few terms and then take the average, so first term, fourth term, second term, so on and so forth, you still remain a skip-free Markov chain, I guess. But can one say how the decay changes? Or?
No, given these sorts of soft results, it would all be the same, whether if you sampled or not. I don't know how. I'm not sure. I'm not sure I answer.
well, my question. So one of the questions I had, I did some similar computations for the Gaussian case, and there you got a parabola, right, for the path.
Yeah.
A slightly different problem is that you start already in equilibrium with your Q.
Yeah.
And then there is the interesting trade-off of being already high at time zero,
Yeah.
because then you have to do less afterwards,
Right.
and building up a lot after time zero.
Okay.
So then you have a kind of interesting variational problem actually that you can
Ah.
solve. And a very
Ah.
interesting feature of that is that you can do exactly
I
the
see.
same in the FBM case, for instance, where you have dependence between where you are at time zero and everything that happens afterwards. So I think one of the questions that you raised at the very end
Yeah.
can indeed be addressed.
Uh-huh.
So the long-range dependent case,
I see. Okay.
though it is going to be tricky.
Yeah. Well, that's interesting about starting in steady state, because it'd be actually
Yeah,
the
you have
probability of a very extreme initial state. Yeah,
Yeah.
that's true.
Yeah, you have a trade-off, and in the Brownian
Uh-huh.
case, you can explicitly compute where you are most likely going to start at time zero. So
I
this,
see. Huh. That's great. Yeah.
if there is no more questions, then let's thank Sean again.